Hello and welcome to the LEGOLAS system. LEGOLAS stands for the Lego-based, low-cost, autonomous scientist, and we'll talk about what this is. Here's a picture at first of the LEGOLAS system. LEGOLAS itself is capable of sample synthesis, measurement of these samples, and then using active learning to decide which samples to create and measure next. This all can be set up and controlled by the experimenter, but uniquely, the experimenter can then leave after setting this up in a closed-loop cycle. LEGOLAS can be used as an educational tool. It is low cost, can be used to teach about robotics, autonomous experimentation and systems, machine learning, and specifically active learning, and experimental design setup. This is a picture of the system. LEGOLAS itself is composed of LEGO Inventor components with an aluminum extrusion frame. It is controlled by Raspberry Pi integrated motors. There are modular components to allow flexible experimental design and incorporation of additional sensors. It can be controlled through a local Bluetooth or Wi-Fi network and can be controlled by Python, in this case a Jupyter notebook. LEGOLAS allows for the integration of various active learning techniques, including Bayesian optimization or exploration, Bayesian inference, live symbolic regression, and any homemade acquisition functions you would like to use. In this case, we will show the robot trying to learn the relationship between composition and acidity. In this process, for synthesis, the robot itself will mix liquids of acetic acid and a solution of its conjugate base, all in low concentrations that are safe. It will then measure the pH using an Arduino pH probe. The active learning segment of this considers several candidate models: a logarithmic, exponential, sinusoidal, cubic, quadratic, and more. It then refines their individual parameters after collecting data. After fitting these models as best as possible to the data, it ranks them on their best fit, taking into account the model complexity and penalizing models that use more parameters. The robot then decides on the next composition to measure, with the initiative of trying to conduct the least experiments possible, when the initiative is trying to refine the model search or rank the models the best. The goal is to recover the Henderson-Hasselbalch equation. This governs the acidity of these compositions within a certain composition range. This composition property relationship can be explored by LEGOLAS, and in this case we would like to discover this constant, a material property associated with acetic acid. We will now showcase the actual task being completed by LEGOLAS. Once the task is started, LEGOLAS will begin by choosing a random composition. As can be seen here, the sample synthesis is occurring. At first, it will take acid, as shown, and then once that desired amount is produced, it will go to the base well and begin adding that to the well. The pH sensor is then dipped in. The cleaning process occurs after measurement. The next sample is again chosen at random. Once 2 data points are collected, we are able to try and attempt to fit the models. As can be seen here, the models with 2 data points show similar rankings in terms of their fit. The acquisition function cannot be utilized until there are 3 data points, so the next point is chosen at random again. To note, the logarithmic model on the graphs on the left is shown by the blue bar. the best model will be the one with the lowest bar. After acquiring our next point, we can see that the models have changed significantly. The model above that dips down quite a lot is the sinusoidal model, and because of the peculiarities of our fitting process, the current candidate rankings show that the sinusoidal model would be the best to explain the data if we were to stop the test at this point. The acquisition function then suggests, using this entropy Gaussian mixture model, that we look to compositions close to the ones we just measured. Once we have the next point, we can see that the models have changed a bit. In the current candidate rankings, the logarithmic model shows the best results. The entropy acquisition function is then changed by this new data and suggests we choose a more basic sample to measure next. This process can be continued for as many samples as is necessary. The last slide here shows the results after just one more test. Again, the logarithmic model shows the lowest bar, and this demonstrates that after 5 measurements, the logarithmic model is believed to be the best to explain the data. It can be seen that the power function also does a good job of explaining the data, but is slightly higher here because of its complexity and the additional parameters that it uses to be fitted to the data. Our top-ranked model is very similar to the Henderson-Hasselbalch equation and shows a pKa, or the association constant of acetic acid, that would be very close to the actual experimentally recorded values.